Welcome to Bio Bits and Bytes. Chronic wounds, the kind that just won't heal, are a massive challenge for so many people.
They really are a significant problem.
Today, we're diving deep into some truly fascinating research. It offers, well, maybe a potential game changer, using incredibly tiny silver nanoparticles.
Right, and boosted by a protein called lactoferrin.
Exactly, all delivered in this clever gel form. We've got a stack of studies here exploring how nanotechnology might just unlock the body's own healing powers.
Especially for these really stubborn wounds.
Our mission today is to really understand the science behind this. How could these minuscule silver particles, teamed up with lactoferrin and delivered in a hydrogel, how could that be such a promising approach?
It's a fascinating combination of materials and biology.
We're going to break down the evidence, see what makes this so exciting. Let's start with the main players. Silver nanoparticles, or AGNPs. Can you maybe define those for us? What exactly are they?
Sure. Well, simply put, silver nanoparticles are just incredibly tiny particles of silver, like really small.
How small are we talking?
We're talking nanometers. So anywhere from maybe 2 up to 100 nanometers. A nanometer is a billionth of a meter.
Wow, okay. That's hard to even picture.
It is. And what makes them so interesting in medicine, especially wound healing, are a few key things. First, they're actually relatively easy to synthesize.
Okay.
Second, you can influence their shape to some extent, but maybe the most important thing is their surface area.
Their surface area?
Yeah, they have a tremendously high surface area compared to their volume. Think of like dust versus a rock of the same weight.
Right, lots more surface on the dust.
Exactly. And that huge surface area makes them super efficient for things like topical drug delivery right onto a wound.
That makes sense. That high surface area sounds like a key advantage for treatment.
Yeah.
Now, how do scientists actually, make these? The research mentions different synthesis methods, including something called green synthesis.
Right. So there are traditional chemical ways using reducing agents, but green synthesis is gaining a lot of ground. It's much more eco-friendly.
How so? What does green mean here?
It means using natural biological sources to actually create the nanoparticles. Things like plant extracts, bacteria, even fungi.
Really? Using plants?
Yeah. And the research shows plants are actually the most common source. Only 89% of studies use them. We're basically harnessing nature to make these advanced materials.
That's pretty amazing. It sounds almost futuristic. The sources also mentioned top-down versus bottom-up synthesis. What's the difference there?
Okay, think of it like this. Yeah. Top-down is starting big and breaking it down. You take bulk silver and use physical or chemical force to get nanoparticles.
Okay, breaking it down.
But the limitation there sometimes is you can get less precise surface structures. Bottom-up is the opposite, building them up atom by atom or molecule by molecule.
Ah, building from scratch.
Exactly. And green synthesis usually falls into that bottom-up category. Those natural agents help convert silver ions and stabilize the nanoparticles as they form.
Building up sounds more controlled, maybe?
It often allows for more control, yes.
Okay, that distinction is much clearer now. So scientists make these tiny particles. How do they actually check they've got the right stuff? How do they characterize them?
Characterization. That's absolutely critical. You need to know what you have. There are several key techniques. One big one is UV-vis spectroscopy.
UV-vis, what does that tell you?
It measures how the nanoparticles interact with light, specifically ultraviolet and visible light. Because their size and shape affect light absorption, UV-vis gives a quick check.
A check for what exactly?
Well, did you successfully make nanoparticles?
Mm-hmm.
And roughly what size are they? Typically in that 2 to 100 nanometer range we talked about.
Okay.
There's a specific light absorption pattern, a peak around 427 nanometers usually, that signals stable silver nanoparticles have formed. It's called the surface plasmon resonance band.
So UV-vis is like a quick first look based on light. Got it. What's another tool they use?
Another really important one is Fourier transform infrared spectroscopy, or FTIR.
FTIR. Sounds complex.
It looks at chemical bonds. Basically, it shines infrared light on the sample and sees how the different chemical bonds vibrate. It gives you a kind of chemical fingerprint.
And what does that fingerprint show in this case?
It helps understand the chemical interactions. For example, how the lactoferrin, that protein we mentioned, is actually binding to the silver nanoparticles. You can see shifts in the vibration patterns.
Ah, so you can confirm the connection between the silver and the protein.
Precisely. And it can even show specific vibrations associated with the silver nanoparticles themselves forming. It tells you about the chemical environment.
Okay, so FTIR gives us the chemical details. What about actually seeing them, their shape and size? Microscopy, I assume.
Exactly. Two main types here. First, scanning electron microscopy, or SEM.
CM.
SEM gives you these amazing high-resolution images. You can see the shape, the size, how they're arranged, the morphology, and how they're distributed.
What did the SEM show for these AGNPs with lactoferrin?
It showed they were mostly spherical. And interestingly, they seemed a bit smaller when combined with lactoferrin compared to the protein alone.
Smaller. Okay. And the other type of microscopy?
That's transmission electron microscopy, or TEM. TEM lets you see even finer details, like inside the particles.
Inside, like the structure.
Yes, their crystal structure. And it gives very precise measurements of their size at the nanoscale.
Yeah.
The studies reported diameters mostly between, say, 11 and 27 nanometers, average around 21, 25 millimeter.
Wow. Incredibly precise measurements. SEM for the overview, TEM for the nitty-gritty details.
You got it?
Okay, there's one more technique mentioned. X-ray diffraction, or XRD. What's its role?
XRD looks at the atomic structure of crystalline materials. Silver nanoparticles are crystalline.
How does it work?
You hit the sample with X-rays and see how they scatter or diffract.
Yeah.
That pattern tells you how the atoms are arranged.
So you can identify the crystal structure.
Yes, and confirm the size of the little crystal domains within each nanoparticle. They even use a specific formula, the Debye formula, to calculate this.
And what did XRD find here?
It found an average crystallite size of about 16.4 nanometers and confirmed the silver has a specific structure called a face-centered cubic, or FCC, lattice. It nails down the fundamental structure.
It's amazing. All these techniques together paint such a detailed picture right down to the atoms. The research also mentioned reaction conditions, time, temperature, pH are important for synthesis.
Are absolutely crucial. Think of it like baking. Change the oven temp or cooking time, you get a different cake, right?
Great analogy.
Same idea here.
Yeah.
Reaction time affects how long nanoparticles have to form. Temperature influences the reaction speed and particle uniformity. And pH affects the activity of the reducing agents and the particle surface charge, which impacts shape and stability.
So you really have to fine-tune those conditions.
Definitely, to get the nanoparticles with the properties you want.
Okay, so we have these well-characterized nanoparticles. Now, the delivery system, hydrogels. What are they and why use them for wounds and delivering these AGNPs?
Right, hydrogels. They're pretty neat materials. Imagine a 3D network, like a scaffold made of long polymer chains linked together.
A scaffold.
Yeah, and this network is hydrophilic.
Yeah.
It loves water. It can absorb and hold a lot of water, kind of like a highly specialized sponge.
And that's good for wounds.
Extremely good. Wounds need a moist environment to heal properly. You need that balance of hydration, oxygen, other factors. The hydrogel helps maintain that perfect little microenvironment.
Okay, creates the right conditions.
And because they're water-based, the silver nanoparticles can be easily loaded in and then slowly released right into the wound bed. Targeted delivery.
So it's like a smart, moist bandage carrying the medicine. The research mentions polyacrylamide hydrogel, sometimes with chitosan.
Yeah, polyacrylamide is a synthetic polymer, very good at absorbing water. Chitosan is natural, derived from things like shrimp shells.
Shrimp shells. Interesting.
Yeah. And chitosan itself has some antimicrobial properties and can help healing, so combining them gives you a potentially more effective hydrogel.
Boosted hydrogel.
Kind of. And sometimes the AGMPs are even made in situ, formed right inside the hydrogel matrix as it's being made.
Oh, to get them evenly mixed in.
Exactly. Ensures good distribution.
So what are the main benefits seen with these AGMP hydrogels in the studies?
Several key things pop out. Strong bactericidal activity, they kill bacteria, which is huge for preventing infection.
Crucial.
Also, accelerated wound closure. These seem to help wounds heal faster. And importantly, in lab tests on skin cells, they didn't show harmful effects. Good biocompatibility.
Kills bugs, speeds healing, gentle on tissues. Sounds ideal. The research also quickly mentions deuterionic hydrogels and anti-fouling.
Ah, yes. Deuterionic materials have both positive and negative charges, but are neutral overall. This makes them anti-fouling. Meaning proteins and other biological stuff don't easily stick to them. In a wound, which is full of proteins, this is useful. If proteins glom onto the nanoparticles, they might not work as well.
So it keeps the nanoparticles free to do their job, like a non-stick coating.
That's a great way to put it. Polycarboxybutane, PCB, is an example. It helps maintain the nanoparticles' activity over time. Very clever design.
It really is. Okay, let's switch gears slightly to the other key player. Lactoferrin, or LTF. What is this molecule?
Lactoferrin is a really interesting protein. It's a glycoprotein, meaning it has sugars attached. You find it naturally in your body in milk, tears, saliva, other fluids.
Okay, it's already around. What's it known for?
It's well known for binding iron. That's involved in iron transport, but also gives it some antimicrobial power by limiting iron availability for bacteria.
Ah, starves the bacteria of iron.
Partly, yes. And in wound healing, it plays a role right at the beginning in that initial inflammatory phase.
Which is a necessary phase, right?
Absolutely. It kicks off the whole repair cascade.
Now, the research highlights a dual role for lactoferrin in the green synthesis of the AGMPs. Can you explain that?
Yeah, this is really cool. When using lactoferrin for green synthesis, it doesn't just stabilize the nanoparticles. It acts as the reducing agent, turning the silver ions into silver metal nanoparticles.
Okay, it makes the silver.
And it also acts as the capping agent, controlling their size and shape, stopping them from growing too big or clumping together.
So it does two jobs at once in the synthesis process.
Exactly. It's a natural multitasker, making the process more controlled and efficient.
That's incredibly efficient. The studies also say these AGNPs, LTF complexes are more robust and even outperform lactoferrin on its own. Why would adding silver boost the protein?
It seems to be a synergistic effect. You get the powerful antimicrobial action of the silver nanoparticles themselves.
Right.
But the lactoferrin seems to stabilize them, make them more biocompatible, maybe even help target them better within the wound environment. The combination is more than the sum of its parts.
Pretty true synergy. Okay, let's dig into the specific biological activities of this combo. First up, antibacterial effects. How well does it work?
Very effectively. Based on the research, it shows good activity against common wound pathogens like Staph aureus and E. coli.
How does it kill them?
Well, the silver nanoparticles can damage bacterial cell walls and membranes, interfere with their metabolism. Lactoferrin adds its own antimicrobial punch, partly through that iron binding.
So a double whammy.
Pretty much. And interestingly, the studies often find it works better against E. coli than Staph aureus.
Why is that?
The thinking is E. coli has a thinner cell wall structure, making it potentially more vulnerable to the nanoparticles' attack compared to the thicker wall of Staph aureus.
That makes sense. Okay, another activity mentioned is antioxidant potential. Why is that important in a wound?
So, during inflammation, the body produces reactive oxygen species, ROS, free radicals.
Which can be bad, right?
In excess, yes. Some ROS are needed for signaling, but too many cause oxidative stress, damage healthy cells, and slow down healing. Antioxidants neutralize them.
And the AGMP-SLTF complex acts as an antioxidant.
Exactly. The research showed, especially at a 4 millimolar concentration, it had significant free radical scavenging activity, much better than lactoferrin alone, actually.
So it protects the surrounding tissue while promoting healing.
That's the idea. Mop up those excess damaging molecules.
Okay, the research also talks about promoting granulation tissue and reepithelialization. Can you unpack those terms?
Sure. Granulation tissue is basically the new tissue the body builds to fill the wound gap. It's made of new connective tissue and tiny blood vessels. It's a good sign of active repair.
The filling material.
Right. And reepithelialization is when the skin cells, the keratinocytes, multiply and move across the wound surface to close it up, like putting the final layer on top.
And lactoferrin helps with both.
Yes, it seems to directly stimulate the cells-involved fibroblasts, which make the granulation tissue building blocks, and the keratinocytes for the skin layer. It encourages them to grow and move.
Wow.
It also boosts production of things like collagen and hyaluronin, key structural parts of the new tissue. So it's actively promoting the rebuilding process.
It sounds like it's really orchestrating the repair. What about inflammation? You said it's involved initially, but also regulates it.
It's a delicate balance. You need that initial inflammation to clean things up and signal repair. But chronic, prolonged inflammation is bad. It hinders healing.
Right.
Lactoferrin seems to help initiate the process, but also has anti-inflammatory activity later on, helping to dial it back down so the rebuilding phases can proceed properly. It prevents it from getting stuck in that inflammatory state.
A modulator, then. Very sophisticated. Lastly, wound contraction.
This is literally the wound shrinking. The edges pull together, reducing the area that needs to be filled in.
And lactoferrin helps with that, too.
Lab studies suggest it does. It seems to encourage fibroblasts to exert that pulling force on the collagen matrix, helping the wound contract.
Incredible. Lactoferrin seems to be involved in almost every positive aspect of healing. So putting it all together with the silver nanoparticles in a hydrogel, the potential seems huge. The research also detailed some animal studies, right? Using rats.
Yes, in vivo studies, they used Sprague Dawley rats, a standard model, created circular wounds on their backs.
And tested different treatments.
Exactly. They had a control group with just the basic hydrogel, groups with the AGMPS LTF gel at different concentrations, 1, 2, and 4 millimolar, a group with just LTF gel, and a group with silver sulfadiazine cream, which is a standard burn treatment.
A common comparison point. And what did they find? What was the outcome?
The standout result was the 4 millimolar AGMPS LTF gel. Wounds treated with that healed the fastest.
Oh, fast.
Complete closure by day 10. Significantly faster than the control group and even the group that got only lactoferrin.
Faster than the standard cream, too.
Yes, it actually outperformed the silver sulfadiazine cream in terms of closure speed in this model. It's a really significant finding.
Absolutely. Any other observations?
They noticed some hair regrowth near the wound in the 4 mm AGMPS LTF group, which suggests it wasn't damaging the surrounding skin tissue, too much low cytotoxicity.
Good sign. What about overall health toxicity?
They monitored body weight. There was some initial loss due to the wound itself, but the AGMP's LTF groups tended to recover or stabilize weight a bit better. And critically, blood tests for liver and kidney function stayed within normal ranges.
So, effective and seems safe topically in the rats.
Based on these tests, yes, no obvious systemic toxicity from the gel application.
That's very encouraging. So, bridging from this preclinical work, what's the potential clinical relevance? Where might we see this used?
Well, the potential is broad. The review mentioned other studies hinting at benefits like silver dressings reducing surgical site infections after certain procedures.
Okay.
And another looking at pressure ulcers in spinal cord injury patients, where AGMP dressings showed a trend towards better healing compared to standard hydrocolloids.
So, hints in other related areas, too.
Exactly. And while these specific AGMP LTF studies didn't focus explicitly on, say, diabetic wounds, the combined properties, antibacterial, antioxidant, pro-healing, make it a very strong candidate for tackling those really difficult chronic wounds, like diabetic foot ulcers.
Which are a huge unmet need.
Absolutely. So overall, the research strongly suggests this combination, especially using green synthesis and hydrogel delivery, holds significant promise for advanced wound care.
It really sounds like it. What would be the logical next steps to move this towards actual patient use?
Well, more research, of course. Optimizing things like the exact AGMP concentration, maybe tweaking the hydrogel formulation for different wound types.
Fine-tuning.
Right? Probably more extensive preclinical studies, maybe in larger animal models, or looking at specific wound types like diabetic ulcers. And then ultimately, you need rigorous human clinical trials
With the gold standard.
to really confirm the safety and effectiveness in people. But this foundational research we've discussed today provides a very exciting basis for those future steps.
Okay, let's try and bring this all together for you, the listener. This deep dive into silver nanoparticles and lactoferrin. It really highlights an exciting place where nanotechnology meets biology.
Yeah, tackling this tough problem of wounds that just won't heal. The potential is really compelling. Faster healing, less infection risk, maybe even better cosmetic outcomes, less scarring.
And it gets really interesting when you think bigger picture, doesn't it? Imagine wound care that's not only more effective, but uses these eco-friendly methods like green synthesis.
Definitely. Combining that green approach for the nanoparticles, the natural power of lactoferrin, and the targeted delivery of hydrogels, it really could be a game changer down the line.
So looking forward, what does this mean? Well, it opens up loads of questions for researchers, right?
For sure. How to optimize the dose. Which hydrogel is best for which wound? How do we tailor it to individual patients? And of course, the big questions about scaling up production, cost effectiveness, getting it into clinics.
Lots to figure out still.
But for you, as someone interested in this area, it's just a fantastic example of how combining different scientific fields, materials, science, biology, chemistry, can lead to potential breakthroughs for real-world health problems.
It really is. Keep an eye on this space. The world of tiny nanoparticles might just hold some really big answers for healthcare in the future.
Absolutely.
Thank you for joining us on this deep dive into BioBits and Bytes.